Hello and welcome to the InfoQ Podcast. My name is Wes Reisz. I am your co-host for the show. Today on the podcast, we're talking to Peter Bourgon. He is a longtime Go developer, the maintainer of the GoKit framework, and is a distributed systems engineer working at Fastly. One of the challenges he's working on at Fastly is data persistence at the edge. Today on the podcast, we'll be talking about state at the edge. We'll talk about topics that hit on things like CRDTs. We'll talk about protocols, things like Raft, and we'll talk about gossip. In general, we'll talk about distributed systems as a whole and some of the challenges in building these systems. Thanks, as always, for joining us on the podcast. Peter, welcome to the show.
Thanks very much for having me. I'm excited to dig into the space.
Yeah, me too. It's been a couple of years. I think New York's probably the last time we caught up, about 2 years ago. You've been kind of deep into this.
Yeah, I kind of was doing a lot of stuff that was like, conference worthy for a while there. And then I took a little bit of a turn and went deep into the guts of some internals, some like infrastructural stuff. And so now I'm just kind of reemerging. My latest project is like a bit more interesting, perhaps.
So why the space? Of all the spaces that you could move into, what kind of made you, and we'll talk about what is edge in a minute, but why specifically the edge space?
Yeah, like what makes this interesting to me, I guess. Yeah, it's like a unique combination of things. One is just that I'm at a high level, like systems thinking, modeling of large scale systems. And so distributed systems in general is a great kind of home for me. That space is like super huge in and of itself. So to winnow it down a little bit, I got really attracted to sort of CRDTs and what I guess is maybe known as coordination-free large scale distributed systems, because they kind of appeal to me in a very almost like aesthetic way. I think it's something about the avoidance of these like highly engineered things like leader election or heartbeats or like all this stuff that's very finicky. You don't deal with that in coordination-free systems. And CRDTs are a great way to sort of like drive yourself there. And it just so happened that at Fastly, there was an opportunity in our product portfolio and in sort of the market for a system that might match all these properties, which is what I talked about at QCon London recently.
So let's dive in. As you know, as we talked about before, I'm working in a similar space with a company called Section. But one of the questions that I constantly get asked when I'm talking to people is what is meant by edge when I talk about edge. In 2018, there was a State of the Edge report that talked about edge kind of divided by the last mile. And it used this idea of the device edge on one side and the infrastructure kind of on the other side of the last mile all the way up to the cloud provider. And that's how I like to try to describe things, device and infrastructure edge. When you talk to people about the edge that you're working on, how do you do it?
Yeah, it's sort of like hipster, right? Because hipster just means somebody who's a little bit trendier than you are, right? And no matter where you sit on the spectrum. And so I think edge is basically the same thing. If you're working in a data center space, then the edge is like anything that's closer to the customer than the data center. If you're a mobile provider, then the edge is like the handset, right? And you might not even consider the junction box on the telephone pole to be edge. Maybe like edge is actually the application in the handset or whatever. So like opinions abound, but I guess like my or Fastly's take on it is influenced a bit by our network topology strategy. And we think the edge is essentially where we sit. So it's a little bit less aggressive of a definition. And to be clear, that where we sit is like our points of presence, which are fewer, but more highly powered than other similar points of presence by other CDN and edge cloud providers in the market. So we tend to plop down bigger points of presence on like internet interchange points, which are maybe a bit more physically distant than other companies in the space, but we can do more there. That's kind of our angle. So for us, that's the edge, which is like away from the customer data center, away from the customer origin, but not all the way to their handset or the telephone pole or something like that.
So let's jump in and start talking about CRDTs, so conflict-free replicated data types. You used a definition, the talk that you referred to a little earlier at QCon London. I don't think it's available yet, but we'll try to push it out and get it out there so people can see it in context of this podcast. But that talk was called Infinite Parallel Universes State at the Edge, and you talked about CRDTs. One of the things that I really, really liked in that talk is you talked a bit about, CRDTs are the data structure plus the operations on how to manipulate that data structure. And you described three properties, associative, commutative, and idempotent. Can you dive into a little bit more about CRDTs and specifically in that context of being associative, commutative, and idempotent?
Yeah, so I guess there's actually lots of ways to define what a CRDT is in sort of a more or less formal grammar. And the thing that always made the most sense to me was kind of an informal definition, which is the one that I try to use when I give talks. And that's the one that you're referring to. The more formal ones are like a joined semi-lattice or something, a lot of Greek letters. It's above my head and above my pay grade as an industry engineer. But what I love about it is it's actually quite intuitive if you sit and think for a minute. So a CRDT is a data type like a map or a linked list or something like this in combination with the operators you can use with it. So like the methods that it supports, the operations that it supports. So it's not just a linked list. It would be like a linked list or like a stack with the push and pop operators. Now, a stack with push and pop is not a CRDT because that combination doesn't satisfy these three things you described. So associativity, commutativity, and idempotence. Associativity, now if I don't have my notes in front of me, I get these two mixed up. One of them is like if you consider addition, right? Like 1 plus 2 in parentheses plus 3 equals 1 plus parentheses 2 plus 3, right? So it doesn't matter what order you do the things in. As long as you do all of them, you get the same number at the end, right? Commutativity is sort of similar. It's like 1 plus 2 equals 2 plus 1. It doesn't matter which one comes first, right? And so that's pretty easy. A lot of operations work that way. The hard part is the idempotence, which means like 1 plus 1 has to equal 1. And of course, that doesn't work, right? It works for like one integer, like 0, right? 1 plus 0 equals, or 0 plus 0. But in general, it doesn't work. So what we would say then is the combination of the data type of an integer and the operation of addition is not a CRDT because although it satisfies associativity and commutativity, it doesn't satisfy idempotence, right?
Just to be clear, idempotence is that property where no matter how many times you apply an operation, the result is the same as if it had only been applied that one time.
Yeah. So then you have to kind of like think a little bit about another way, another data type and another operation that might be kind of like addition, let's say, but would be idempotent. And the thing that I think is most intuitive is if instead of you have an integer, you have a set of integers, like classic set theory, and instead of addition, you have union, then it kind of works out, right? Because like union would be like a set containing the integer 1, union, a set containing the integer 2, union, a set containing the integer 3, right? You can see this is like associative and commutative. That's kind of pretty self-evident. But then the fun part is the idempotence, right? Because the set containing the integer 1 unioned with itself just gives you itself, right? And so that's really cool. And as it turns out, like, yeah, you wave your hands and do a bunch of math. You can leverage these three properties in like super, super interesting ways that basically from the perspective of a distributed systems designer means I don't have to care about keeping track of a lot of stuff that I would otherwise have to care about keeping track of. I can just kind of like throw these operations at each other. And if there are all these like fallacies of distributed computing, if the network's down or slow, or I have partial outage or blah, 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 all this stuff is fine. As long as I continuously make a good faith effort to like move the state of the system forward, it's all going to work out. And this is, I don't have to do any special engineering to make that happen. It's just an invariant property of the CRDT. And so if you can build a system out of these building blocks, then like the engineering work you have to do to like deal with faults, basically not completely goes away, but like mostly goes away. And I think like, at least for me, that's the future of this space.
Let's do a bit of an example. So we talked a bit about CRDTs, but to kind of give it contextualized, to kind of help someone kind of visualize how a programmer might use this, and specifically in the context of maybe a key value store at the edge, how might you use a CRDT? Like there's this concept, last rider wins. What does that look like in context of a CRDT?
So a lot of the examples so far have been very specific, like a set of integers, right? That's great if you're, doing stuff with integers, but often if you have a key value store, you want to be able to store like arbitrary information, which in CRDT world means you can't necessarily leverage any semantics, any properties of that information to make your job easier, to resolve conflicts or whatever else you want to do. Often all you get is this big blob of bytes and you say, okay, how do I make this useful, right? So the important property that we need to maintain, I think at a very high level, is this idea of like deterministic mergeability. So an example I like to use is if you have a whole bunch of operations that users have done to the same logical key in a key value store. The important thing, and this is what associativity, commutativity, and idempotence give you, is if you put all those operations in a big bag and you shake it up, this is a magic bag. So when you shake it, it actually duplicates some of the operations that are in there as well. So you shake it up for a while and then you pour them out, and you pour them out in some order, right? The important thing is that when you apply all those operations in whatever order with whatever duplicates, you get to the same end state, regardless of how it happened, right? And you can do that a million times and you always get to the same end state, assuming the same bounded set of operations. So that's what we need, right? And if you just have a big blob of bytes, it's difficult to do that by itself. So one simple solution is to use something called a last writer wins register. Okay, what is that? Well, you take your blob of bytes and you attach almost like a timestamp, but it's not really a timestamp. It can have a time component to it so that you have some sense of total order, but it's really more of like a monotonically increasing UUID. So every node in the system all over the world is going to have its own like generator of UUIDs. This is kind of like a Lamport clock or a vector clock if you've heard those terms before, but it's not really, it's fundamentally different. And so every time a write happens, you can attach a little timestamp to it. And when you go to merge these values together or like put them in the big bag and shake them up, the winning write, the one that is the winner at the end, is the one with the biggest timestamp. So it's like really simple, right? Like the largest timestamp wins, last writer wins. And you can do some funny stuff with the timestamps to make that, smarter. But that's basically the idea. Now, what this means is that if one of your nodes is having a clock that's like way off and way in the future, it's going to be like winning all these contests, and the overall state of the system will be, deterministic, but it won't probably be what your customers want, right? Because you can set as often as you want over here in New York, but if this wacky clock in Tokyo, if someone's doing something there, it's always going to win. It's always going to be the right that succeeds. So like that's a problem, but it does give you this nice API where it's just like set and get. Single value set, single value get. Okay, so that's like one naive way to do this kind of thing. And a simple API. And we think like that's going to be great for a lot of use cases where you don't have like a ton of write volume. But if you want to get a little bit more sophisticated and want to really leverage sort of the causal history that these sort of systems can give you, there's this thing called a multi-value register. Maybe I invented this. I'm not quite sure, actually. Anyway, it leverages this thing called a dotted version vector set. And I won't get into the math, but sort of at a high level, instead of just doing a set and you give it a value, you do a set, you give it the value, and then you give it this thing called a causal context. And a causal context is sort of a compressed history, a compressed graph almost, of all of the operations that have occurred on that key up to this point. So if you imagine Alice sets it to 1, Bob sets it to 2, Charlie sets it to 3. When I set it to 4, I need to include something that has Alice with an arrow to Bob with an arrow to Charlie.
It's like the event stream of the change.
Yeah. Basically like that, right? And it's compressed reasonably well. But what it allows you to do is say, okay, as the system, I see now David set it to 4, and he already like baked into that value of 4 is Alice, Bob, and Charlie's operations as well. And so I know for a fact that since David has seen Alice, Bob, and Charlie's operations, he has incorporated them into his operation of 4. And so I can make much more intelligent decisions about how to merge things together with this information, kind of like alongside the actual value.
Yeah, so it's like, I don't know, event stream, almost the blockchain of the change that actually...
In a way.
Yeah, that's interesting.
But what it does mean is that if you have a value, so imagine if 2 people made different writes from the same like point in history, and then like a blockchain fork, right? Other people kept making changes based on their changes. And then at some point you want to try to merge them together. Well, when you do a get, there is no single answer. There's like actually 2 answers or more, or 7. And so the get actually returns multiple values. And you have to, as the application author, decide which one is right and then write back a single answer.
Do a merge.
You have to do a merge. That's right. It's up to the application is kind of the answer. Like it depends on what you're doing.
Frameworks in the past just kind of handled all these tricky things. Now we're having to start to think about this at the application level and be able to make decisions given that we have multivariant values coming back.
Exactly. Like if we want to have all these nice properties about latency and responsiveness, but also like not deal with conflicts in a way that is like coherent, we're going to have to make the applications more complicated a little bit, at least.
So, okay, let's apply what you just described in the context of kind of edge computing. So again, points of presence in like that infrastructure edge, that middle tier that sits between the cloud provider and like that last access, again, my definition, but you've got all of these kind of points of presence globally spread out. And so you're building a system leveraging CRDTs to kind of maintain like a key value store at those areas?
Yeah, so you touched on a couple of things, which I think it's important to like shine a bit more light on. Like most people, when they design systems, they're doing it often for like systems in a single data center. And the properties in a data center are like pretty good. Like you have pretty good connectivity. If something goes down, it's like a major crisis. A lot of people are immediately fixing it. Everything's fast. Everything's reasonably reliable. And most importantly, everything's really physically close, right? So the latency for information to move from one part of the system to the other is pretty low, like orders of nanoseconds or microseconds or something.
You're not dealing with the speed of light, right?
Yeah, there we go. There it is. For me, at least, the main constraint in edge system design is that you can't ignore the speed of light anymore, right? The logical system that you're trying to build occupies a physical space that is subject to like Newtonian, physical laws, which we like as a function of the constants of the universe cannot cheat. And so we have to move away from this kind of classic Newtonian model of physics, which worked really great at the kind of data center scale. And we have to start thinking about the speed of light as a core invariant to our designs. It's sort of like almost in a sense shifting to the quantum model of state manipulation. Yeah, so for me, like that is the core constraint of designing in this space. And also like the faults that come with it now, we can't really ignore or we have to treat a lot more seriously. And so CRDTs to me are like the thing that allows us to think productively at this scale, right? We can't keep falling back to the same circuit breaker patterns or retry loops or leader election when we're not sure that the messages we're going to send to other parts of our system are even going to get there in a day. And we're talking about speed of light on the planet Earth now, but like it's not inconceivable that in the near future we're going to be designing data systems that need to go interplanetary, and like all of this becomes even more important.
Yeah, I haven't gone there yet, but yeah, I can see it. So let's talk about other approaches, I guess, when you're trying to maintain state and maybe why they may not work. Like, for example, speed of light is one of the things that may be one of the challenges on, say, doing Raft or something between these things. But if you've got a group of servers and you want to maintain that consistency, there's things like a gossip protocol, there's things like Raft. So let's talk through some of those. Raft is an approach where you basically elect a leader. There's a heartbeat that gets sent out that has, 100 milliseconds, 50 milliseconds, something like that. So right there, Raft doesn't really work in this kind of situation for the edge that you described because of that speed of light problem. Is that accurate?
I would say so. Practically, yeah. I mean, you can tweak the timeouts in a Raft installation. And like in theory, you could make it work at a large scale. But you have to bear in mind that every operation you do, if you're doing like strict Raft, has to go through a full quorum, meaning it has to like go out to the leader. It has to like go through a round. It has to get appended to the log, and then you have to get the response back as a client. And all those things are subject to the timeouts. So if you have a timeout that's big enough to accommodate a global scale kind of consistency model, then by definition, your latency for the user is going to be probably unacceptable, like on the order of seconds for every operation.
Before we start jumping into things like availability and consistency, it might be good to kind of recap CAP theorem.
Yeah. Broadly, it states if you're designing a distributed system, you can either choose so-called availability or so-called consistency in the face of a partition. Now, a partition is just a network fault. And the important thing is they happen all the time. You can't avoid them. They're inevitable, like death and taxes. So you have to choose what happens when they happen. And Raft says we choose consistency, right? And there's a whole set of protocols like Raft and Paxos. There's a whole family of protocols that you can use to do this. But because of these latency requirements, they don't really work outside of, a single data center, let's say, roughly, if you want to have reasonable latency.
There's something else that you hit on there that I think it's worthy of describing with the problem that you're addressing. You're talking at the request level. So it's like every request that's coming through, you're wanting to, check the state for that key value store. For an example, you're not talking about hundreds of requests that all then may go back to a single item. You're talking at that request level. Is that right?
Yeah. Are you trying to distinguish that from something else?
Yeah, I'm trying to distinguish it like with what you're trying to do is do this lookup every time. So that latency is added on every individual request. It's not something that you can pay once and then use 100 times.
Right. I mean, it depends on the type of system you're modeling, right? But I guess for the purposes of discussion, let's say key value store. Obviously, every time you want to write the value to something new, you would expect that information gets shared and is consistent across the system by some definition of consistency. So writing is kind of intuitive, like you need some kind of global consistency at some level. But even reads, actually, you need some kind of formal definition of consistency. Like it's okay maybe if you read stuff that's out of date, but you shouldn't read something that's flatly wrong, right? That has been rendered inconsistent by something else you read previously. And so now we're getting back into this like formal language again, but there's whole classes of serializability and linearizability, which these different consistency models get you. Yeah, so Raft and what I just described with like the round trips and all that, this is like one of the more formal ones. And then in so-called AP systems, or choosing availability in the case of a partition, also like these are known as eventually consistent systems. And to be clear, that's what CRDTs give you, is an eventually consistent system. You can have things that are out of sync. You can sort of do some operations offline for a while and have them all be really fast and have them kind of like sync up later. And importantly, CRDTs and some other like properties make sure that that overall process is still like formally consistent. It's still correct is probably the right way to say it. So that's important to keep in mind.
A system like Cassandra would be an AP system.
Yeah, Cassandra is like a pretty well-known AP system, although I'm not like super familiar with like all the ways that it communicates. Like I guess there are different ways to configure it, and you can make Cassandra clusters that are like very physically large and probably have different ways of configuring the various interchanges that way. But yeah, I haven't used Cassandra in Anger, so I'm not sure how much I can shed light on that.
So we talked a bit about Raft, Paxos. So on that kind of AP system, we talk about gossip. So why not gossip for problem at the edge here?
This is actually quite interesting because it gets into a slightly different aspect of system design, which is like data ownership or data location, let's say. So maybe we can set the context a little bit about the physical systems that we're describing here. So in any sort of like edge compute system, the whole point is that you have a bunch of physical servers or devices that are kind of spread out across a large physical space. And so often what you want to do is sort of establish a single logical state space, let's say. So every customer wants for example, a key value system where if they set a key on a device over here, they can get it on a device over there. And it's the same logical thing. Okay, that's fine. The other constraint is that these devices are often like not huge. And so you can't really keep the entire data set on every device. You have to do some kind of like heuristic. You have to either have it in a central place that you can refer to, or you have to spread it out somehow based on use or something like this. Again, it's like a physical constraint of these types of systems. And so this begins to like inform the design of like data ownership. Like if you set a key to a value in some place, I guess that it has to live on the device in that place to start, but where does it go eventually? And if another device somewhere else requests that key, how does it get it? Like, what is the protocol? What is the information hierarchy? How do you make the request and make it be successful? And making it all the more complicated is like, how do you do that in the acceptable latency bounds, essentially? So gossip is one way for information to flow through a system. There's lots of like gossip protocols, and they all kind of guarantee that the information will propagate throughout the network eventually. And many of them establish like upper bounds on how long that can take. But often those upper bounds are like quite long and kind of have a long tail. And this is often like not super compatible with kind of the requirements of real-time key value stuff. Like it's okay maybe if it takes a second to go on the other side of the globe, or maybe even 10 seconds. But if you say it'll get there, within 6 hours, probably, like statistically, that's probably not going to be acceptable to your customers. So I'm like glossing over a lot of like advanced stuff that's happening in the gossip space right now. It may not be quite this dire, but in summary, gossip presents some challenges to like addressability, let's say, or like data locality. So, I mean, like that's one extreme, I guess. And maybe another extreme is something we're more familiar with, which is like how typical database replication works, like read replication, let's say.
We talked about AP systems, we talked about CP systems in kind of context of the edge. Now, one of the things that I also like in this talk is you kind of talked a bit about the project that you're working on at Fastly and how you're thinking about the problem of kind of state and how to model it. And you kind of talked about this hub and spoke type of system. Can you talk a bit more about that?
Right. And this is exactly that data locality thing, right? Like given you have a customer who's writing a key over here and someone who wants to read the key over there, how do you move the information in a way that is like efficient and respects all the constraints that we laid out? And so I don't know, like there's a million ways to answer this question actually, and I'm not sure any of them are correct. But if on one end of the like spectrum, you have gossip, and on the other end, you have this like strictly hierarchical, single write primary, multiple read secondary kind of database replication model, then maybe, at least this is where I landed, there is a space in the middle, a point in the middle, where each sort of site, each sort of node in the edge terminology is its own like fully realized store of state. And maybe the way that they communicate with each other is through a centralized, what I call an upstream. So one way to think about this is like hub and spoke. You have one sort of like centralized upstream that all the sites connect to and regularly communicate with and kind of sync up the state that they've experienced in the last bit of time with the upstream, and then sync down anything from the upstream that they might not have heard about yet. And so hub and spoke is one way to think about that. It actually turns out that you can extend this, and it actually is just like an n-ary tree. You can kind of build these up fractally. And what that gets you, I think, is kind of the best of both worlds. Like each site can be physically constrained, only this much RAM, this much CPU, whatever. And the upstream can be kind of like in the cloud, let's say, where, disks are free and infinite, or however that works. I don't really know.
When you say n-ary tree, though, you mean so like one pop might have another pop, that just different upstreams that could be literally chained together, so to speak.
So like every pop has precisely one upstream, but the upstream itself can be considered like a pop that can also have an upstream.
So they can chain together, so to speak.
Yeah, exactly.
But within the actual pop itself, you can kind of model the characteristics of like a CP system, or more of a like raft almost, kind of consensus is strong.
If you wanted to, you could do that. And that's not how we do it at the moment, although it certainly could be a strategy. Yeah, the main point is that within a pop, everything's physically closer. So you have more leverage, more like breathing room in terms of what kind of access patterns you want to use. Yeah, so that's kind of the model. And I guess the other important thing to like point out is that to satisfy the recency bias. So like to put this in easy term, I guess like a pop, a site, a device shouldn't have data that it doesn't need, right? So if no one's ever requested a key, it shouldn't be there, right? And so I can get into it later if you like, but we have a way of doing this. And what this does is turn the system kind of into like an LRU cache, essentially, of like the most recent stuff, but with an authoritative sort of like, in a sense, origin or upstream where everything lives, and you can get it if you need it.
Yeah. So basically, if you haven't requested it in 20 minutes or something, it's not going to be there, or whatever that interval may be.
That's right. Yeah.
So the system you describe kind of reminds me, as you're talking, a bit about Console. So Console uses, in kind of global distributions at least, Console will use maybe Raft within a cluster, and then it uses more of Gossip protocol between them. Is that similar to what you're talking about?
I think if you squint and kind of back away, yeah. In the sense that I think any sort of globally distributed data system of any type is going to it's going to converge towards the same sorts of architectures. Just like all supercars essentially have to, for aerodynamic reasons, have to basically look the same once they start going a certain speed. I think the architectures are basically going to look similar. Yeah. So yes, I would sort of like point out some distinctions here, I guess, between Console and this system. And I guess the main one is that Console is meant to be a system of record. In other words, you put authoritative information in there, which it keeps safe, right? That's its whole reason for being. And so that informs the design kind of at a very fundamental level. That's why it uses Raft internally. That's why I don't know the details of like the site-to-site kind of communication link, but I'm sure that they also keep that kind of at the forefront. That means that you're often going to pay a latency penalty, even in a site, to set a value, right? Because it has to confirm that everything has seen it. In my system, since it is an LRU cache, and since we have an authoritative upstream, and since much more important than this level of consistency is the latency, then we make different sort of engineering decisions. And this is actually maybe worth highlighting. So everyone's into edge compute now, right? Amazon got it started with Lambda, I suppose. And then there's cloud functions. And now all the like former CDNs are getting into the space. At Fastly, we have this computed edge initiative, which was sort of the origin of my project. And I can say a lot about it, but what I really want to highlight is just that we use WASM, WebAssembly, and sort of a novel compiler and runtime to run customer code in the HTTP request cycle in the CDN, right? And so more than anything else, we are bound by latency for all this stuff. We cold boot and run everything on the order of like single to double digit microseconds for the code. And so any sort of like state component to this system has to be, let's say an order of magnitude in that space. And so even Console, like configured as tightly as possible in the best possible network, I think you're still looking at double digit milliseconds to do writes, which is, like just a different class of system.
Okay, so like fundamentally what we're talking about, hub and spoke system plus CRDTs to be able to kind of like have a what is the valid state kind of resolved by the actual data structure itself. Applying all that together, what are some of the, I guess, trickier problems you're running into on the implementation of this? Where are the sticky bits?
Yeah. I mean, like if you listen to me talk in the first part of most of my talks or this interview, you think it's like, that's such a rosy picture. All the problems are solved.
It's easy. All talks are at conferences, right? It's like, oh, wow, everyone's architecture is amazing. Mine's awful.
It worked perfectly. Millions of requests a second. No, there's a couple of like fundamental problems with CRDTs that are actually like at the moment, I would call them even unsolved. The first one you touched on, which is like size, right? In order to get all these nice properties about, automatic mergeability and correctness, and it doesn't matter what order anything's in order to get all those properties and still have like useful data types, like not just a set of integers, for example, you have to pay a cost of size, like bytes in memory. There's a lot of duplication or like, let's say, data amplification. So if you have the simplest possible key value, which is maybe just like a set of bytes, if you want to store like, I don't know, a megabyte in there, depending on how big your overall network is, that could balloon to 10, 50, 100, 1,000 megabytes, depending on the techniques you use. So obviously you can't charge the customer for this kind of thing. So there's like a natural tension there. Like, how do you get it small enough while still maintaining all the properties you need and, keeping the system live? And this is hard. Like every CRDT based system has to grapple with this at some point. And a lot of systems that would be commercially viable aren't because of this. And so that's like something that's top of mind for me. We do cheat. We have to cheat in clever ways in order to make this tractable. And that's going to be an ongoing bit of engineering. Hand in hand with that is like not having to do leader election and quorum and like all these typical distributed systems things. That's great. But the way we then deal with faults is simply by replicating our communication. So taking full advantage of this idempotence property, which means that often we're going to be putting a lot more bytes on the wire than we strictly speaking need to be. So Fastly and Edge Cloud CDN companies are pretty well positioned for this. We have pretty good networks, often with a fair amount of overhead, but that's not always true. And, it's another constraint that you have to be careful of. And I think the final one, which is maybe the most important, is that if you're developing an app, right, you really want there to just be a database, right? And you do an insert and a select and it just kind of works. And you don't want to think about the speed of light or how to model your state layer if there are conflicts or something like this. You want the sort of database or the system to take care of that for you. But as I mentioned kind of earlier, like that's the Newtonian model of state, right? That's the simple model. And what we're doing now is kind of stepping into the quantum model, the complex model, where you can't just make that assumption anymore. You have to start thinking about state conflicts in the application. The state system, in order for it to like be useful in this way, it's going to expose this stuff for you, this kind of like internal stuff for you. And the APIs, like more concretely, the APIs that it gives you are going to have not just set and get, but like set with a causal context. What is that? I don't know, but I have to keep track of it. And like get doesn't just return one value, it can return multiple values. And it's like, okay, what do I do with that? So like in short, I'm not sure the market is like totally ready for this, especially like a lot of applications that want to work on more classical, simple state paradigms. So a lot of my job is going to be making that tractable, like easing people into APIs that take full advantage of all this stuff without scaring them away. And to the best of my knowledge, that's not really been done obviously successfully yet. I think the closest we came was Basho in their React database. They had CRDTs as a first order thing, but they're kind of barely around anymore. So I don't know. That's a hard part too.
So sets and maps and hashes were the good old days. Now we're talking about data structures that are CRDTs, that are probabilistic programming practices, that our data structures are becoming much more advanced, much more, I guess, intuitive on the systems that we're building.
We got to follow them into the sunset like that.
Yeah, but hopefully people like you are making them nice and easy for us to be able to leverage and use.
I'm doing my best.
So your talk, Infinite Parallel Universes, State of the Edge at QCon London 2020 should be out here in a few weeks. So look for it on InfoQ. You can dive in a little bit deeper. You can actually see all the hand wavy stuff that he was doing, actually describe it in visuals. In addition to that, if somebody really wants to go to next steps, short of just saying Martin Kleppmann, what are some of your recommendations on some things to look up for CRDTs?
Yeah, it's a great question. And like going back to the very beginning of the conversation, one of the things that draws me to this part of the industry is that it's also like cutting edge in a way. There's no CRDT book, right? Almost immediately, if you're going to want to learn more, you're going to be reading, academic papers that have come out in the last 10 years, right? That's kind of the state of the area of research right now. So I can basically just name names and you can search those people and you can kind of see where their research and blog posts and often like Twitter streams can take you. There's a lot of interesting like individual articles and individual things that I can encourage people to look at. So Martin Klettman is a great one. He's a researcher at Cambridge, I believe. Anyway, somewhere in the UK.
Yeah, Cambridge.
So he did a lot of academic work in the space and is now working on something called auto-merge, which is a attempt to get CRDT semantics backing up basically a JSON object. There's some like work there and people are porting that to all sorts of interesting things. So that's a great thing. Professor and a colleague in the space of mine, Carlos Baquero, is on the cutting edge of a lot of CRDT research. The most recent thing that I really got into with him is so-called delta CRDTs, which are kind of addressing the size and bandwidth sort of problems that I mentioned a little bit earlier. Christopher Meiklejohn is another guy who is working in the space. He's working on, as far as I know, a programming language called LASP, which brings all this stuff into the programming language level, kind of built on Erlang with that kind of programming model. And I think you can learn a whole lot from Cal Kingsbury and his work with the Call Me Maybe Jepsen testing series. So he takes these databases, commercial databases that claim to have, whatever consistency mode, and basically proves that they don't largely and quite often. But in so doing, in the process, you learn a lot about this sort of like serializable modes, linearizable modes, all the different ways of accomplishing all these things I'm describing and how different tools and components and systems kind of fit into the overall spectrum. But yeah, like I wish there was a book. The area is just too nascent and I think moving too quickly to like point anyone at any specific thing.
Very nice. Peter, as always, it's awesome to chat with you. Thank you so much for joining us on the InfoQ Podcast.
Yeah, it was my pleasure. Thanks for having me.